All right, a lot to cover here in day 11. We're going to start chapter 12, start looking at circles and lots of properties and different theorems. I might have to make a video of some of these problems and hopefully upload it by Friday. Okay, so we're going to get straight into it. We're going to look at tangent lines. A line is tangent to a circle if it intersects or crosses the circle in exactly one point. Okay. Um, So this is an example right here, right? Point B, or this line AB, is tangent to the circle at point B. Okay, now I know because of the ink and the way that it's drawn, it looks like there are multiple points of intersection, but it's not. Okay, B is called a point of tangency, and AB is tangent to circle C. Okay, um, a theorem from that, right? If AB is tangent to the circle at P, then the radius, right, from the center to that point of tangency is always perpendicular. Okay, this is going to be pretty important even later on in the chapter. And so a couple examples here. First of all, lines that it tells you in the directions, right? Lines that appear to be tangent are in fact tangent, and O is the center of the circle. Okay. All right, and so hold on. And so here we know that's 90 degrees, okay? And this quadrilateral. Quadrilaterals always add up to 360. Number two, you've got a right triangle here, okay? Um, and in number three, it looks like, so there's a equilateral triangle within it, but we're going to use this central angle 60, then this is 90 degrees, and this x over here, right, to make 180. All right, here we can use the Pythagorean theorem because we know it's a right triangle. Okay, so x squared plus 14 squared is x plus 10 squared. Okay, so using some algebra here. Okay, so you got to remember how to double distribute and FOIL. Remember, this is not x squared plus 100. Okay, it ends up being x squared plus 20x plus 100. Okay, and you can use Pythagorean theorem over here also. Okay. This is one of those where I might have to make a video, okay? Which is tangent to circle G, right? If the radius is 4, and so you actually have to try the Pythagorean theorem 3 times to see which one works out, all right? Then there's another theorem, okay? If from point B, right, you have these two segments, if BA and BC are both tangent to the circle, right, then those two segments are actually congruent, okay? Meaning the distance from A to B is the same and C to B are the same, right? And so here, again, I believe we can say and assume that there are points of tangency. We set these equal to each other because they are congruent, all right? Gotta use some algebra solving skills here. A couple of vocab words, inscribed versus circumscribed, right? Um, the triangle is circumscribed about the circle, right? It's around the circle, right? The circle is inscribed the triangle, right? It's inside. Okay, so gotta know those. And so we have these kinds of problems where I think if you look at the blank notes, it might be a little bit more. Um, you'll be able to understand more what they're asking for here, right? What is the perimeter of each polygon? Okay, so um, you know these are congruent, okay, because there are points of tangency, right? That's the theorem that we just learned. Okay, so sometimes I know right now this is all filled in for you, but if you look at the blank notes, that might be a better idea to go try some of those, okay? The pulley problem. Okay, so let me go a slide or two ahead. I'll come back to this slide. So these are what pulley problems look like, okay? I know it looks confusing, all right? Like this, okay? But it's actually not that bad, okay? If you follow these directions, draw the segment of the centers, right? So we connect the centers, right? A to B, and it says draw the radii to the points of contact. Okay, so this is what I drew, right? These red lines here. Those are the radii to points C and D. And then it says through the smaller circle, draw a line parallel to the common tangent. So I drew this green line here, right? So from the smaller circle, right, I'm going to draw a line that's parallel to CD, right? And so we draw this line here, okay? And so what happens is we know that what we're essentially drawing here is a rectangle, right? Because this is 90 degrees. Remember, from the radius to the tangent line, that's always 90 degrees, okay? So that's 90 here and 90 here, and these are parallel, okay? So these are 90 degrees. And so what happens is this ends up being a right triangle, okay? It ends up being a right triangle. So I'm going to make a video going over numbers 12 and 13. So be on the lookout for that. Okay. I think we're heading into 12.2 now, all right? There are theorems relating each of these three things as congruent, all right? If I think we did these before, okay? If you have a central angle, right, then the intercepting arc has the same measure, right? They're congruent. And also, you have these chords, right? A chord connects 2 points on a circle, right? It's a segment, all right? And so if the central angles are congruent, then the intercepting arcs are going to be congruent. So here DE and arc D prime E prime. And the intercepted segment, the chords, those are going to be congruent as well. All right, as long as the central angles are congruent. Okay, and so we've got a few problems here. I think for number one in the blank notes, you're only given this 90, okay? But you know that if the chords are congruent, then this must be 90. This arc is 80 degrees. And then you have the leftover arc, x, right? Well, we know a circle is 360, right? So that's why it's 360 minus 80 minus 90 minus 90 to get 100, okay? Half a circle is 180 degrees. And if these arcs are congruent, then the central angles are congruent. So if this is x, then this must be x. And then for this one, for number 3, again, if this arc is 60 degrees, then this central angle here is 60 degrees. So it creates a 30, 60, 90 triangle here. All right, take a look at this theorem too. Okay, I know it's a little bit hard to read here, right? If OE is congruent to OF, all right, then that must mean that those chords are going to be congruent. So AB is congruent to DC, right? And conversely as well, right? If AB and CD are congruent, then that must mean that OE is congruent to OF as long as those are perpendicular, right? Equidistant, okay? So some examples here as well, okay? How do we solve for x, right? If they're both 3, right? That's a big clue because I think in the blank notes you don't have this 8. But if this is 8, and remember these tick marks mean that they're congruent, so this must be 8, so therefore the whole thing must be 16. Okay. Take a look at examples 5 and 6 as well. All right. And there's a bunch of stuff here. Okay. You might have to pause or look at the blank notes here. All right. If AB is a diameter, right, and AB is perpendicular to CD, then what happens is you have CE and ED, okay, those parts of the chord are congruent, as well as CA is congruent to AD, right, those arcs, okay. Yeah, read through these theorems here, right? Again, I might make a video, another video going over these, okay. 12 theorem 12.9 is just the converse of 12.8, right? If you know that a diameter bisects a chord, right, then that means that it has to be perpendicular to the chord. Okay. And then this theorem 12.10 here, in a circle, if the perpendicular bisector of a chord contains, or in a circle, the perpendicular bisector of a chord contains the center of the circle, meaning it just goes through the center of the circle. Okay, and so here, a few examples to look at. All right. We can safely assume that this is 4 because of the fact that it's 90 degrees, right, to this chord, right? And so it splits the 8 in half to 4 and 4. Right? Same thing here. If the chord is 10, then it splits it to 5 and 5. Now the thing is, I believe, if you look at the blank notes, all right, you actually, where I'm highlighting here, you actually don't have this line, okay? But you can actually draw it in because if this is the radius x, then this is also the same radius x, right? And so we need that so that we can draw this right triangle in order to use the Pythagorean theorem. Okay. And so we kind of did the same over here, all right? I know, we used x, but we also, the y is half of that x, okay? And so if you can figure out that half, then you add it all together to figure out what that x is. All right, and so and some arc problems, all right, using the properties, okay, congruent chords. If congruent chords, then congruent arcs, okay? All right, so if the chords are 16, and if arc CD is 108, that must mean that arc AB is also 108, okay? If this is 90 degrees and if these are tick marks, they're congruent, that must mean that these angles are 45 degrees. Okay. And if the central angle is 45 degrees, then this arc is 45 degrees, which means this whole thing is 90 degrees. All right. Sometimes you might have to use some trig here. Okay. All right, and take a look at these problems as well. Right, again, double distributing. Right, this one I might make a video for number 14, so be on the lookout for that. All right, I'm gonna stop here and make another video. Take a look at part 2 because I'm running out of time.